This is the video for section 3.6 notes, slides 26 through 29. All right, in section 3.6, we're talking about inverses of functions. Now, I know we've already talked about inverse trig functions, logs and exponentials, which are inverses of each other. But in section 3.6, we're talking about functions just in general and their inverses and how they behave. So this is related to a common type of question that you're going to see in the notes here. All right, so first of all, we need to do a quick little review of functions in general and their existence of inverses. So take a look at f of x here. Looks kind of like a parabola, like x squared plus 1 or something. All right, so if we reflect this graph over the line y equals x, you'll see that this new graph, this reflection, is not a function. It fails the vertical line test, right? And so we say that, well, the new graph is not a function, so f of x does not have an inverse. Now, remember, I said f of x is like x squared plus 1, right, just for this particular one. So what would its inverse be? Well, the fact is that if we solve for the inverse, remember, this is where, like in pre-calc, we say, okay, put y in, and then switch x and y, so x equals y squared plus 1, and then we solve for y, so we subtract 1 and square root. So the fact is that y would equal plus or minus the square root of x minus 1. And so you have the positive half of the square root and the negative half of the square root. So this is two functions. So we can say f of x does not have an inverse because it would have to be split into two separate pieces. All right, but over here, g of x, all right, g of x would be this graph here, and this would actually be like x cubed minus 2, right? So if that was g of x, all right, then we would say, well, this does have an inverse because its reflection, if you look over here, follows this, and it is a function. So it would pass the vertical line test. And so we could say that this new graph here we would call g inverse of x. Now, of course, I gave you this x cubed minus 2, right? But it doesn't really matter what it is. It doesn't matter if we even have any idea what the function is. If it is a one-to-one function, then it will have an inverse. Now, what is true about a one-to-one function? So let's take a look at this one over here. Okay, you'll notice that the derivative is negative, then 0, then positive, right? Over here, the derivative is positive, 0, positive, right? And so the fact is that if the derivative of your function is greater than or equal to 0, or less than or equal to 0, then it is a one-to-one function, and therefore will have an inverse. So moving on to slide number 27. All right, when does a function have an inverse? Well, number one, the function passes the horizontal line test, or the slopes of the tangent lines do not change signs. So f prime of x is greater than or equal to 0, or f prime of x is less than or equal to 0. It can equal 0, right? Remember in the last problem, the x cubed, right, goes here. It does equal 0 there, but it's positive here and positive here, so it's never actually negative. So it never changes sign. All right. Or what we could say is the function is strictly monotonic. Monotonic meaning it has one tone, or it's always increasing, or it's always decreasing, right? And so if the function passes the horizontal line test, which means that the slopes of the tangent lines do not change signs, which means that the function is strictly monotonic, then we can say that there will be an inverse. All right. So on to slide number 28. All right, so it says show that f has an inverse by showing that f is strictly monotonic. Well, what does that mean? Well, we just said it on the previous slide, right? That the slopes of the tangent lines do not change signs, or the function passes the horizontal line test. So function passes the horizontal line test. Well, that's a graphical method, and so just drawing a graph isn't always the best, but number two is very good. So basically, if we can determine that f prime is either greater than or equal to 0 or less than or equal to 0 for all x, then we can say that f is strictly monotonic. So in other words, let's find f prime of x. All right, so f prime of x, 9x to the 8th plus 35x to the 6th. All right, so 9x to the 8th plus 35x to the 6th. All right, if we put any value of x in, what are we going to get? Well, x to the 8th. Well, that's going to be a positive number. So 9 times a positive number plus 35 times a positive number is going to be positive, unless we plug 0 in, which would be 9 times 0 plus 35 times 0, so that would equal 0. So f prime is, in fact, greater than or equal to 0 for all x. And so, since this is true, we can say that f is strictly monotonic. All right, next, slide number 28. So f prime of x, well, what's the derivative of cotangent x? Well, negative cosecant squared x. Right now, this is between 0 and pi. All right, so let's think about negative cosecant squared. All right, so there's a negative, obviously, times cosecant of x quantity squared. So remember, x has to be between 0 and pi. Well, actually, there's a typo there. X should be between 0 and pi, but not including 0 and pi. Why is that? Well, because cotangent has asymptotes there, so that's actually a typo. But let's think about it. For any value of cosecant, so between 0 and pi, that would be quadrants 1 and 2. Remember, cosecant is the reciprocal of sine. So if I take sine in quadrants 1 and 2, what do we get? Well, we always get a positive, but we're squaring it. So I guess it wouldn't really matter. If we're squaring it, it's always positive, and then times a negative. So what can we say? F prime of x is always less than or equal to 0. Do we have to include the equal to? Cosecant can never be equal to 0, right? Because when sine is 0, cosecant is undefined. So in this problem, we can say f prime of x is strictly less than 0. So f is strictly monotonic. All right, that's slide number 28. All right, on to slide number 29. All right, so now here's an interesting thing. All right, we have if a function if a function f of x has a point at a comma f of a, then its inverse has a point at f of a comma a. Remember, x and y switch from a function to its inverse. All right. So what about the slope, or the slope of the tangent, or the derivative? Well, the slope of f at a, so f prime of a, is the reciprocal of the slope of f inverse at, well, a. Well, remember, what we have to realize here is that the slope 1 over f prime of a, these are inverses. But for this function, we refer to this as f inverse prime of, well, what's the x value? It's actually f of a. So that can be confusing. So let's look at a picture. All right, so if I have a picture here, I always will draw something like that. All right, and so I've got my dotted line showing that this is a reflection. All right, and so what I want to do is I want to pick a point. So let's say I pick a point somewhere on, let's say on f, so this is f, and then I have f inverse over here. All right, so that means the corresponding point would be about here. All right, and so what I want to do is I want to imagine the tangent line. So here's the tangent line here. Let's draw that a little better. All right, tangent line here and the tangent line here. What slopes do they have? Well, you can very clearly see they're both positive slopes. All right, they're not equal though. All right, these are certainly going to intersect somewhere, right? All right, and so what the fact is that let's say that this first slope is like 1/2, and this slope would be 2, right? They are in fact reciprocals, not opposite reciprocals. All right, so the key here is that the point on the left is a comma f of a, and the point on the right then is f of a comma a, right? The x and y switch. So it's important to note that the derivative, okay, on the left would be f prime of a. So what would the derivative on the right be? Well, it would be f inverse prime of f of a, right? Remember, it's the x value of f of a, so it's the derivative of the inverse of f at that particular x value, which happens to be f of a. All right, so that will be very helpful in looking at this. So it says find f inverse prime of 1 if f of x equals 2 cosine of x. All right, so what I do is I always draw. It doesn't matter what the function is. I'm always going to draw a picture that looks like this. Okay. And then I'm going to label. So this is f, and this is f inverse. Now, important to remember, okay, if I have 2 cosine x, this is in fact a monotonic function from 0 to pi, right? Okay, so like if I think about cosine from 0 to pi, that would look like this, right? Now, I drew it like this because I'm going to draw every picture like that, all right? But it is true that cosine would have an inverse on that interval, all right? All right, so now I'm going to label these points. All right, so it says find f inverse prime of 1. So 1 is the x value on f inverse, okay? Which means 1 is the y value on f. All right, so now the question is if 1 is the y value on f, then what's the x value? Well, that means f of x is equal to 1, which means that 2 cosine x is equal to 1. So that means that cosine x is equal to 1/2, which means, well, if cosine is 1/2 on 0 to pi, that means that x is pi over 3, right? So the x value is pi over 3, and that means the y value over here is pi over 3. All right, so now if I want to find f inverse prime of 1, what does that mean? So that means f of a is 1, okay? So that means that I want 1 over f prime of not 1. 1 does not go here. Look at f. The point is pi over 3. So that would be 1 over f prime of pi over 3. So now, to answer this question, I need to find f prime of pi over 3. All right, so f prime of x. All right, so f is 2 cosine x, so f prime would be -2 sine x. And so I want to evaluate f prime of pi over 3. So -2 times the sine of pi over 3, which means -2 times the sine of pi over 3 is √3 over 2. So I get -√3, which means that f inverse prime of 1 is 1 over -√3. So of course, if you rationalize, you would get -√3 over 3. All right, and so that is slides 26 through 29.